Hello, my name is Jenny. Today I'll talk about my study on the exoplanet TOI-1107b. Before I start, I want to acknowledge my advisor, Dr. Ian Crossfield, and my graduate mentor, Alex Polanski. I believe that you all are somewhat familiar with our own solar system. From the inside out, the 8 planets are Mercury, Venus, our planet Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, all orbiting around the Sun. But when we look into the night sky, we can hardly not wonder if there are more than just that. Are we alone in the entire universe? How do all the planets form and stay where they are right now? Are they all the same type? Or how will they end their lives? That kind of lead to the first section of exoplanets. Before the research on exoplanets became popular among astronomers, our solar system had always been assumed to be a typical planetary system. Starting from the beginning of the 21st century until today, however, as more than 4,000 exoplanets have been confirmed, many previous assumptions on planetary systems are challenged. Now, what is an exoplanet? Well, exo, originally from Greek, indicates outside or beyond. So exoplanets simply refer to the planets that are outside of our solar system. Shown in the exoplanet populations diagram on the right-hand side, we typically classify exoplanet into 5 main categories. For those giant planets like Jupiter and Saturn, we have hot Jupiters and cold gas giants. Then for those rocky Earth-like planets, we call them rocky planets or lava worlds. And for the planets that have Neptune's mass, we call them ocean worlds and ice giants. And finally, the great triangle at the bottom right corner marks the region where very seldom exoplanets that have been discovered. Now let's move on to the methods we use in detecting exoplanets, typically transit and radio velocity measurements, and some detailed analysis on my planet of interest, TOI-1107b. First, transit means a planet passes in front of the star and blocks some lights that are emitted by the star. As you can see in this figure, the apparent brightness of the star is obviously smaller during the transit time. Of course, seeing a decrease on apparent brightness does not always mean a planet is transiting, because there are just so many other things in the space that can pass in between a star and us. However, if we're able to observe the same feature happening in a steady period, it is highly possible that there is an exoplanet. Then what can this curve tell us? Well, because the planet is physically blocking the light, the depth of the curve is directly related to the size of the planet. And using this equation, we'd be able to calculate the radius of the planet. Another feature on the curve is the width, starting from the decreasing of the brightness until the end when the brightness gets back to normal. The width of the curve directly tells us the duration of transit. The instrument we use in measuring transit is called TESS, or Transiting Exoplanet Survey Satellite, which was launched in 2018. Pretty straightforward, TESS measures the brightness of the star and seeks potential exoplanets. Now let's talk about TOI-1107. Without the small letter b, this is the star's name of this planetary system. And you can basically find it somewhere close to the South Pole. The figure on the right-hand side is the transit measurement done by TESS. You can clearly see about 8 to 9 complete periodical transit happening, which highly suggested that it should be an exoplanet transit. From this curve, we get a very accurate transit period, which is a little bit longer than 4 days, with only 4-second uncertainty. If we zoom all the way into one transit, you can see a much familiar figure as I've shown in the previous slide. By fitting a best fit transit curve, we calculated the size of the planet to be 1.23 plus or minus 0.06 radius Jupiter, and the duration of the transit is about 4.5 hours. Another method we used is the radial velocity measurement. We know that planets orbit around the star, Well, but the fact is that the planet and the star orbit around what is called the center of mass, which is marked by this blue cross in the middle of this diagram. In our solar system, the sun is so massive so that the center of mass actually lies inside the sun. Therefore, we don't really see the sun moving back and forth. However, when the planet, like TOI-1107b, is massive and moving fast enough, it can cause the sun or the star wobbling. What we can directly measure is the spectrum of the star, which is this rainbow colors shown in the figure. Now, because the star is moving a bit toward us and then away from us, the spectrum shifts to the left and right along with it. And this back and forth movement of the sun or the star is caused by radial velocity. And at the bottom of the screen, I have the equation for calculating the radial velocity of the star. But don't panic about such a long equation. What we really care about are the mass of the planet and the eccentricity of the orbit. So after a task measures the transit light curve and reports a potential exoplanet, we follow up and try to characterize it using Minera Australis, which is a ground-based exoplanet observatory located in Queensland, Australia. The figure shows the radial velocity curve of TOI-1107, where the amplitude tells us the radial velocity, which is about 320 meters per second. And the sinusoidal curve tells us that the orbit of the planet is very circular, thus the eccentricity is basically zero. We use the long equation shown in the previous slide. The mass of the planet is determined to be 3.02 plus or minus 0.37 mass of Jupiter. And thus, with the size of the planet and its total mass, we also calculate the density of the planet to be 2.04 gram per centimeters cube. Now, we can move on to the significance of TOI-1107b and the study on exoplanets in general. We first fit TOI-1107b as well as Jupiter and Earth into some pre-generated plots from NASA Exoplanet Archive to help visualize the statistic. On the left-hand side, I put the exact same exoplanet population diagram, highlighting the TOI-1107b in red, Jupiter in brown, and the Earth in yellow. In this figure, you can clearly see that TOI-1107b lies exactly in the hot Jupiter category. So basically, you can consider TOI-1107b as a Jupiter, but orbiting its host star in a very short period and typically being very hot, roughly speaking about 1500 kelvins, since it is very close to the star. The figure on the right-hand side is plotted with mass and radius, which are the two most important characteristics of planets. And you can see that even the non-Jupiter-like planets, TOI-1107b is still one of the biggest and most massive planets. So for lower massive stars, as mass increases, you can see that the radius increases with it. However, for those massive planets like Jupiter's, their gravity gets large enough to compress materials, and thus the radius stop growing with mass. Then why are we particularly interested in TOI-1107b? So far, there are 4,575 confirmed exoplanets, which is far from enough for astronomers to understand any of the questions I proposed at the beginning of my presentation. This literally makes the analysis on every single exoplanet important, so that we will be able to study the formation and evolution of exoplanets statistically. Meanwhile, as a hot Jupiter, TOI-1107b is another candidate for future study on this group, including temperature, atmosphere, chemical composition, migrations, etc. For the field of exoplanets, since we're limited by detection technology, the majority of exoplanets being observed are still large planets with short period, which is unfortunately a big bias. So with more observations done by TASS and the soon-to-launch James Webb Space Telescope, we hope to explore the frontier region on the exoplanet populations diagram and dig deeper into the secrets of exoplanets. That's all for today. Thank you for listening.